Fisher projection to the cyclic structures that we have shown here on the very bottom. The first thing we're going to do is take the Fisher projection and have it fall over. Here's falling over to the right. And to keep the right stereochemistry, all of the hydroxyl groups that we're pointing to the right, so it's 2 and 4 in this case, and 5 that we're interested in, all of those are going to be pointing down when the Fisher projection tilts over. Any hydroxyl group that's pointing to the left is going to be up at carbon 3 here. Then we did this stepwise to help put this hydroxyl group that's here in the back and carbon 5 in the right position to form the cyclic hemiacetal. We rotated with the blue bond around carbon 4, 5, that bond, carbons 4 and 5. That now situated this hydroxyl group so it can act as a nucleophile, close the ring. And then I explicitly drew the step where we're first going to protonate the aldehyde's carbonyl group, just like what we've seen with the previous reactions. So we protonate this species here. Then we actually have our nucleophilic attack, closing the ring, forming this structure down here in the bottom right. We've noticed we've generated a chiral carbon here. And then, so in terms of the chemistry, we just had to deprotonate this hydroxyl group, this oxygen, I should say. We deprotonated that to generate this sort of a product that we have here. And then we kept track of the stereochemistry because we generated a chiral carbon. This, I should point back to one more in the middle. This hydroxyl group can kind of come in from the bottom or from the top of this carbonyl containing carbon. And that's going to generate these two stereoisomers that we had. And right now we just use the language of down and up. So any questions about that? I know that's the multi-step process that we're going to go through here. Okay, so then a little bit more with this is a bit more jargon that goes along with this. And one is that if this hydroxyl group here, so if the OH group is cis to the CH2OH, and so you'll notice that these two groups, I'm going to use magenta, hold on. These two groups are cis. This is known as the beta isomer. And if the OH group here, I'm missing a hydrogen, I just noticed. If the OH group is trans, meaning they're on opposite side of the ring, so it's trans. We'll slide up now here. It's trans to the CH2OH. Then that's going to be the alpha. So here, this one and this one, they're trans to each other. That's alpha. In this case, on the right, they're both on the same side. That's the beta conformation. So this would be known as beta, indicating the stereochemistry at that one center. These are both D sugar, they're D sugars they were to start with. So this is known as beta D glucopyranoside. And this would be alpha D. I don't expect us to memorize those names, but a pyranose, this pyranoside, comes from this six-membered ring with the oxygen in it. One more bit of language is that this carbon here, we're going to see is a special carbon. This carbon here, it's the hemiacetal. And this carbon is known as being the anomeric, anomeric. It's the anomeric carbon. And so these two sugars here, they only differ at the one particular chiral center, that's the anomeric carbon. So one other thing is they'd be known as anomers. of each other. So a lot of language, a lot of new ways of drawing things. I think I saw a partial part of the question in the chat, but it didn't all show up.